Okay, hello everybody, and welcome to another session of our AmSul webinar on differential geometry. As always, you can see in our chat the links and web pages where you can join the WhatsApp group and follow us in YouTube. Okay, after that, let me introduce you the speaker of today's talk. He's Emilio Lauret from Universidad Nacional del Sur in Bahía Blanca, Argentina, and he will speak to us about isospectral spherical space forms of highest volume. Okay, thank you, Emilio.
Okay, thank you, Adrian, for the presentation and the invitation. I will talk about two collaborations. One is with Benjamin Lenovitz, that is already published this year. And the other is a very recent preprint from last month, or probably August, in collaboration with Alfredo Alzaga from Bahía Blanca, that is also attending the talk. Okay, let me start with something quite simple in some sense. A space form, let's recall the definition, is a complete Riemannian manifold of constant sectional curvature. Okay, it must be constant. And well, the Killing-Hoff theorem ensures us about this space that the universal cover of one of them, let's assume that the sectional curvature, because it's constant, let's assume that is equal to -1 or +1, because if you scale, you can obtain it. So if the sectional curvature is equal to 1, constant equal to 1, then the universal cover is the hyperbolic space, n space, if we assume dimension n. And more or less the same with the other cases, right? So if you have curvature 0, constant curvature 0 is the Euclidean space, and curvature positive, or remember, we will assume it's going to be 1, the curvature, is the n sphere, okay? And this is the case that we are going to focus. They are called spherical space forms. And equivalently, to say that the Riemannian universal cover is this one, because we are assuming that the metric is the canonical in these three cases. Another way to say this is that there is a discrete subgroup, discrete, and we are going to be interested in this case, okay? And because the isometry group of the sphere are the rotations in the Euclidean n+1 dimensional space, this is compact, and discretes will be equivalent to finite in the case of n spheres, okay? And okay, if we have a discrete subgroup in general of the isometry group of the universal cover without fixed points, this is in order the quotient is a manifold, satisfying this, okay? Our every space forms can be written in this way for X, one of these three spaces, okay? And gamma coincides with the fundamental group, okay? So let me state the question that we are interested in this talk. Let's assume the hyperbolic space, n-dimensional space. You fix one with finite volume, okay? We said every space forms, hyperbolic space form is of this form, so let's assume that it's written already this form, and you take a subgroup of this gamma, since this gamma acts without fixed points, gamma prime, any subgroup also does it. And we have that the volume of this is given in this way, okay? So if you have finite subgroups of finite index, you will have that your volume is going to increase the number of times that the the index. Okay, you increase the volume, and it's a natural and important question in the hyperbolic setting. Is what is the? This is the first time that we assume compact, but we can omit it in this part. What is the hyperbolic space form of finite volume, say, or compact, as you wish? It's not equivalent in the hyperbolic case. With smallest volume, we want to have, remember, the curvature is equal to -1. We have rescaling in some way that is -1. And well, this is a natural question, very difficult. Misha Belolipetsky from IMPA studied from an arithmetic point of view. I mean, for certain hyperbolic manifolds, arithmetic is very related with number theory. And well, in the Euclidean space, you don't this question doesn't have any sense, right? Because if you have any Euclidean space form, I mean, for instance, a compact flat manifold, you rescale the metric, and you will still have constant curvature 0, right? This is not true in the if you rescale something with constant curvature equal to -1, the curvature will change, okay? But in the case the curvature 0, you can rescale, and it has no sense the smallest or highest volume, because you can have any volume as you wish. And in the spherical case, the question has sense, but it's obvious, because remember any discrete subgroup of acting by isometries in the sphere is finite. So the volume of a spherical space form written like this is going to be the volume of the sphere quotient by the number of elements in gamma. Okay. And the analogous question asks for the highest volume, not the smallest, the highest volume, the largest volume. But the answer is obvious, is the sphere itself, right? Is when gamma is the trivial group. This responds the analogous question here. But here is something that it has sense to ask in analogy, that Benjamin Linovitz and John Voigt studied in the hyperbolic setting the smallest, the pair of isospectral hyperbolic manifolds with the smallest volume. Okay, let me wait until the next slide about the rigorous definition about isospectral. But roughly speaking, is the Laplacian have the same spectrum. And they studied this question in the hyperbolic setting. So this question has the following analogy: natural analogy in the spherical case is to look for isospectral pairs of spherical space forms having highest volumes as possible. Okay. Of course, we assume non-isometric in order that this has sense. And this is a question that we study with Benjamin Linovitz. It's a paper that actually we studied several questions and problems in the hyperbolic settings, and we studied in the spherical case. Okay, this is only one of the 4 or 6 questions. I don't remember. This is only one of them. Okay, and let me now define what means isospectral. In any, very, very roughly, in any Riemannian manifolds, we have a very distinguished differential operator, is the Laplacian, the Laplace-Beltrami operator. And we will assume that all manifolds are compact from now on. So the spectrum of a compact Riemannian manifold is the collection of eigenvalues of the Laplacian. Okay, the collection of eigenvalues is just this, the eigenvalues. And well, It turns out, because the Laplacian is self-adjoint and more properties, that the spectrum is, it might be complex, the eigenvalues, but they are real, they are non-negative actually. The zero is always there because the constant functions are eigenfunction for the eigenvalue zero. And well, the rest are numbers that increase, okay? They don't have accumulation points in the real line, only at the infinity, okay? This goes to plus infinity when k goes to infinity, if you order it this way. Okay. In particular, any eigenvalue can be repeated finitely many times in the spectrum. The spectrum is a multiset; it's not a set. Okay, like the spectrum of matrices. Some element might be several times in this collection. This is not a set, a multiset. Okay. So, two compact Riemannian manifolds are said to be isospectral if they are spectra coincide. Okay. A paper, a very famous paper that popularized this problem is Can One Hear the Shape of a Drum, using a physical interpretation that the spectrum encodes in some way how a drum or a Riemannian manifold sounds when one hit it. Okay, that's the idea. I will not talk much about this. And well, let's say that there are certain spectral invariants. Okay, there are some things that the spectrum determines about the geometry of the manifold. For instance, the dimension, the volume. This will be very important for us. Well, the dimension too. The total scalar curvature. Okay, and a few things more, much more complicated than the previous three. Okay. So, in order to start giving details about the main question, remember we are looking for the highest volume possible of isospectral spherical space form. Okay, I will omit saying non-isometric because it's redundant. And note that if you wish the volume as high as possible, you need the group gamma as small as possible. Okay, the number of elements in gamma should be as small as possible in order to have the volume as large as possible. Are there questions so far? Please interrupt me when you want.
Emilio, yes, I do have one. You're considering the Laplace-Beltrami operator only on functions?
Yes, only on functions, absolutely.
Okay.
Yes.
Thank you.
Thank you. Okay. So, let's talk about the classification of spherical space forms. Remember, are a complete Riemannian manifold with constant sectional curvature equal to 1, not only positive, equal to 1. So let's fix one of them. And if this is the boring case, because the only even dimensional spherical space form are the sphere itself and the projective space. And that's all. There is no one else. Okay, up to geometry, there are only two. So let's assume the dimension odd. And if you pick gamma non-cyclic, the classification is quite involved. It was done by Joseph Wolf in the 60s, late 60s. It is in the famous book, Spaces of Constant Curvature Spaces. No, Spaces of Constant Curvature, that's the title. And okay, this is very nice. Actually, my student Mauro Colantonio is working with them. But in this talk, we will not care about these groups, non-cyclic fundamental groups, because now that with Benjamin Linovitz, we proved that if you have two isospectral spherical space form with one of them with non-cyclic fundamental group, well, the other one also will be non-cyclic. This was proved by Aikida, actually. The number of elements, of course, are the same because the volume is the same. We say that the volume is an spectral invariant, so the number of elements is also an spectral invariant. But the point is this one. The number of elements of the fundamental group is going to be at least 24. Means that the volume, we have an upper bound for the volume. Okay? And well, we will, if we find in some dimension some spherical space forms with fundamental group cyclic and a pair of them isospectral with at least 23 elements, okay, then we will know that the highest volume is realized in a length space and not in one of these elements. This is what we are going to use in the rest of the talk. And moreover, in order to convince you that it is not necessary in this problem to work with non-cyclic, at least in the results, the smallest order of the known isospectral cases, examples already known, is 275. Okay, it might be possible to increase because I haven't found any other, but I couldn't prove that there are no spherical space form isospectral with order less than this, with the fundamental group not cyclic. Okay. Okay, so let's concentrate in length spaces. Okay, length spaces are spherical space form with fundamental group cyclic. Okay, cyclic. In collaboration with Roberto Miatello and my PhD advisor and Juan Pablo Rossetti, we work a lot in the spectral geometry of these spaces. And well, let's assume that the order of the fundamental group is Q, and any of these spherical space forms, any of these length spaces, can be written in this way. There are parameters and integer parameters. These parameters are prime to Q, or co-prime to Q, all of them. In such a way, this length space is isometric to this quotient that we are going to denote like this. This quotient. You think that here should be n 2n minus 1, sorry. The 2n minus 1 dimensional sphere you identify with the n complex tuple of unit null. Okay? This is the 2n minus 1 dimensional way to realize this unit sphere of dimension. And we are going to relate two elements in the sphere in this way. Okay? In this way. You are acting now that this is a co-root of unit, a primitive co-root of unity, because S1 is coprime to 1, so this is primitive. Each of them is primitive. Okay? These are primitive co-root of unity. And well, the quotient is our space. Okay? And we have this very well-known proposition that yields that these length spaces are isometric if and only if we have this condition. That is very short but quite difficult to understand. Okay, let me explain. Let me stop a moment here and explain what means. I mean, forget for a moment or assume that this t is 1 and forget this. This is plus. Okay, so this is telling us that we can permute the parameters, right? Permute the parameters, and yes, of course, because this means that you can permute the parameters here, and of course, geometrically speaking, this will be an isometry. Okay, there is no change if you permute these coordinates, right? And here there is a mod Q the mod Q, what means? Well, of course, if you sum to S1 some multiple of Q, this number will be the same, so it doesn't affect at all to the axiom. And well, if you put now a -1 here, let me change the color. If you put a -1 here, you fix the rest. You put the permutation, the identity, and so on. But put a -1 there. Is like a -1 is going to be there, and this is the conjugate. So in these two planes you are reflecting, and this is again an isometry. Okay. And changing the number t is just changing the because t is coprime. This is my way to say is coprime to q. Is like you are changing the generator. So the quotient is the same, not isometric. It's the same, directly the same. Okay. So the point is that these three ways to do this, you obtain isometry. The main point of the proposition is that these three ways are the only ways to produce isometric length spaces. For instance, let's play a little bit. Suppose Q is equal to 2. Okay, remember this model Q means it is not necessary to work with high parameters. It is sufficient to work with parameters from 1 to q minus 1 actually. Okay, and when q is 2, 1 is the only parameter, so you have only one length space, and actually this length space is the projective space. Okay, let's increase the q, the number of elements of the cyclic group, to 3, for instance, and well, you have only one because these are all isometries. Okay, because you put 1 and 1. If you put 1 and 2, okay, remember you can multiply each coordinate by -1, but -1 is equal to 1 model 3, so it's the same. The same with this isometry, and this isometry, the 1, 1 isometric to 2, 2, is because you are multiplying by 2 all the coordinates and you get the isometry. Okay, so you have when q is 3, the number of length spaces is only 1. Here also, only 1. But when q is larger, this is not the case anymore. And for instance, when you have 3 coordinates, remember, if you have 3 coordinates, the dimension is 2 times n minus 1. So in this case, it's 5. Okay, so the 5-dimensional length spaces with fundamental group of order 7 is isometric to 1 and only one of these 3. Okay, this is a representative set up to isometry. Okay. Okay, are there questions? So remember, we are interested looking for isospectral spherical space form with highest volume means smallest fundamental group, and the fundamental group will be a length space, so it's going to be cyclic. And here I will introduce a main lemma to produce many of them, but let me introduce some notation. We were working, remember, with n tuples, right? These coefficients are n vectors of vectors of length n of integer numbers. Okay, let's think this vector as list, like in Python. Okay, you have in Python list, and in Python you have this operation concatenation that you sum two lists and produce, well, the larger list with the elements in both lists. Okay, and you can multiply the list and you repeat the coefficients. Okay, and this is one part of the notation, and the other part is, let's fix an integer number q. This will be the number of elements of your cyclic group, of your fundamental group, and q0 is going to be, now that this is the phi, Euler phi totem function, right? The number of coprime numbers to q model q, or the order of this group. this number over 2. This will be Q0. And take T of Q is going to be some Q0 numbers in order, if you have this number and their opposite, they form a representative set of the units in set Q. Okay? Yes, a representative set. None of them are congruent module Q among this set of two Q0 elements. Okay? Now that 2 times Q0 is the number of units set Q module Q. Okay? For instance, in 9 you have to put 1, 2, and 4, and that's all, because the rest of coprime numbers, 5 is minus 4, and 7 is minus 2, and 8 is minus 1. Okay? It's not necessary because you put the minus there. So the lemma that we discover with Benjamin is the following. If you have isospectral length spaces of some fixed dimension, this dimension means that this has n coordinates. Okay? If you have any pair of length spaces, let's assume non-isometric also, then these two new length spaces are again isospectral and non-isometric. And what is that? Okay, to our n coordinate, we sum to both of them, we sum here, there are Q0 coordinates, and R times Q0, okay? And we did it to both of them the same, okay? The only difference between these two length spaces is still the coordinate of S and S prime that were here, all right? So these new length spaces are again isospectral and non-isometric. And what is the point? Is that the dimension increase, right? Because the dimension, what is the dimension? Remember the dimension, it was twice the number of coordinates, and the number of coordinates is this one, minus 1. Okay, and when you, this is not correct, right? The number of coordinates is n plus r times Q0. That's correct. And when you have 2n here, you have minus 1 here, and twice Q0, remember, is the Euler phi function, phi Euler function, so you have this. Okay? So you increase the dimension. You can increase the dimension of isospectral spherical space form. And well, let's review the very first examples of isospectral length spaces. This was done by Aikida in 1980. At that moment, there were not many isospectral examples in general among Riemannian manifolds, only flat tori and hyperbolic surfaces by Vineras were known. And well, Aikida presents these very simple examples. These are the coefficient of the smallest coefficient as possible. I mean, you have three components, so the dimension is 5. 2 times 3 minus 1, 5. And the number of elements is 11. Okay? And these are, one can check that they are isospectral and non-isometric. And the proof was very clever, actually, but we cannot talk about this now. And the main lemma, increase the dimension, ensures that these new length spaces, when Q is 11 here, so a representative set of zeta 11 is 1, 2, 3, 4, 5, and their opposite. Okay, and these new length spaces, whose dimension is 10 times r plus 5. If you do if you compute the dimension, is this. These are isospectral and non-isometric. Okay, and remember, we are looking for pairs of a spherical space form with highest volume as possible. Okay, and here comes our first main result with Alfredo Alzaga. We prove that if two length spaces have order Remember, if two length spaces are isospectral, they must share the same order. Okay, the fundamental group must share their orders. Okay, so if you have two length spaces with fundamental group of order 10, they cannot be isospectral without being isometry. Okay, the only isospectrality is the trivial one, is when they are isometric. Okay, if you have less than or equal to 10 elements, you cannot give you cannot have isospectrality, truly isospectrality. Okay, and this theorem implies that these examples have highest volume as possible. Okay, because less volume than the volume of the sphere, the dimension 10r plus 1. This these length spaces has this volume, and one cannot have less volume because of this theorem. Okay, so this theorem solves the problem for every dimension of the form 10r plus 5. Okay, it's solved for all these dimensions. And moreover, here comes a table. Let me explain a little bit the table. Here is n. N is the number of coordinates. Remember the dimension. Remember the dimension is 2n minus 1. Here is the number of coordinates. And here comes the q, okay, the number of elements of the fundamental group. And the table explains as follows. If for this entry, for instance, has a cross, because there are elements of dimension 2 times 3 minus 1, there are length spaces with q equal to 11 and this number of parameters that are isospectral and non-isometric. These two, okay? Every time that there is a cross is because there is isospectrality among length spaces of this fixed q and this fixed number of parameters. Okay. If there is a dash, there is no any isospectrality. If the q doesn't appear here, for instance 14, is because there are no any in any n. Okay, in any n that appears here. Okay. And if there is a cross, a tensor symbol, let's say, right? This circle cross means that this is the isospectrality with q as small as possible, because this table was done with the computer. You can, for if you fix n and q, you always have finitely many length spaces, and with the computer you can compute all of them, and you can compute whether they are isospectral or not. Not for an arbitrary n and q, but for small values you can do it. And this tensor symbol means that the volume is as high as possible. It's the highest possible. Okay, this is the highest possible. This is the highest possible, and the same, because we check that. For well, I mean, now it's a theorem that you cannot have with at the most 10 elements isospectrality, okay? But we didn't know at the beginning. And well, this is the table that explains this. And the idea is that in order we prove that, and now that we did the table until 43, because remember, non-cyclic fundamental group, spherical space form that are isospectral and their fundamental group are non-cyclic will have at least 24 elements. So if you get any length space isospectral here, is because the highest volume is going to be attained in length spaces. We are sure about this. And well, another corollary of our main theorem, that is the first main theorem, that is this one. We prove that Suppose you have this, the volume exactly, or it has exactly 11 elements in fundamental group. Okay, if you sum 5, you sum this Q0, you again have this. You again have, I'm sorry. You have this, and you have this, and you have this. Okay. For instance, here, if you have this isospectral pair and you sum Q0 to the number of parameters, you again have an isospectrality here, and this is what the main lemma ensures. Okay, if you have this, okay, I think it was clear. But the main point is that thanks to, let me clean everything. If you, let me use the blue, no, the red one. You have this. Okay, they coincide with this, and this. So you pick any of these three of them, and you sum 5 parameters to the n. For instance, this, you have 12, and you can prove then that in any of these dimensions, the volume will be exactly this one. Okay, the small of isospectral spherical space form, right? The number of elements must be 11, the smallest as possible, in order to have isospectrality in this dimension. Okay, so we prove in these cases, and the computer can prove this, but for infinitely many cases. The main point is that we did it for infinitely many because R here is any positive, it must be 0 also, but any natural number. Okay? Okay, are there questions? Let me continue with the table. And this is the theorem in collaboration with Linovitz, is previous to this one. And what happened here? Okay, you take any isospectrality, not necessarily the one with less number of the least number of elements. Okay, you take anyone, you take this one, and then you sum 9 to 4, so you have this, and you sum 9 to any of this number, and you have always, this is this row, you will have always for every n congruent to these numbers, this, now that here is 3, 4, 5, 6, 7, you have all these, but you also have here 2, and here 3, and the 8 and 9, I guess it appears here, and these 2. So you always have isospectrality in these dimensions. Okay? For this number of parameters. Remember, the dimension is 2n minus 1. You always have isospectrality of length spaces. In this paper, we were interested whether the isospectral spherical space form of highest volumes are realized as length spaces. Okay? And well, since the number of elements in this table is less than 24, any length space realized here produce infinitely many length spaces of infinitely many dimensions. The dimensions respond to this condition. Okay, so we obtain this using this table. We obtain all these conditions, which are a lot, but it is not enough to say that the highest, the isospectral spherical space form of highest volume are always attained in length space. There are always exceptions. For instance, until n equal to 1000, you have 2 exceptions. And moreover, we did this table until 63, and we get a lot of more conditions, but still have everything with the computer, right? We still have exceptions. The first exception was 30,000 and something. And well, it is necessary some new idea because computationally it's not possible to solve it in this way. And well, this is our best ugly, but our best statement as we did. Okay. And okay, let me change a little bit the setting. Remember, a space form always is in this way, and we assume that gamma acts without fixed point. But now let's relax this condition. And gamma now is a discrete, finite subgroup of the isometry group that may have fixed points. May have fixed point. No, not necessarily with fixed point, okay? And the quotient is an orbifold. It doesn't have the differential manifold structure anymore, but it's an orbifold, and the tool that we have, or the notion that we have used, extend to orbifolds in a natural way. In particular, the Laplacian and the volume, everything goes in the same way, so the questions have sense among orbifolds. What is the main difference is there are many more orbifolds than manifolds. Why? Because the condition of acting without fixed point is very strong. Okay, the spherical space form are not many as the number of groups acting by isometries. Okay, in the spheres. So the question will be, what is the largest volume among of isospectral spherical orbifolds? And the second main theorem of the article with Alfredo is the following. The highest volume of a pair of isospectral spherical space form is equal. In this case, we were able to prove exactly how much is in every dimension from phi. And it's equal to this. What means this is there is we show a pair. Okay, let's explain in detail. How we prove it? Well, we use an example, very smart example done by Rossetti, Dorothy Schut, Juan Pablo Rossetti from Córdoba, Dorothy Schut from Berlin, and Weiland, I think it's in Florianopolis. They constructed a pair of almost conjugate, non-cyclic, almost conjugate subgroup of SO6. So this group acts in the sphere of dimension 5 with 8 elements. Okay, this is the 8 that appears here. And well, they prove, they constructed, because Tsunada's method is something I will not explain, but Tsunada's method implies immediately that the quotient, they did it with v equal to 5 here, but it is easily extendable to any dimension, that they are isospectral. They are isospectral, okay? So we have already an upper bound for the highest volume, okay? Because we obtain an explicit example with 8 elements, so we have this. And at the same time, we prove with Alfredo that if you have at least 7 elements, it doesn't matter if gamma is cyclic or not. It acts by isometries in the d-dimensional sphere, but doesn't matter this if you have at least 7 elements, and you have both 2 of them with at least 7 elements, such that the quotient are isospectral, then the groups are conjugate, and this means that the orbifolds are already isometric. Okay, there is no isospectrality if you have 7 or less number of elements. Okay, among lens orbifolds, among spherical orbifolds. Okay, so 8 is the best value, the maximum, the minimum number of elements possible to produce isospectral spherical orbifolds. Okay. And well, 48, I wanted to talk a little bit about the proof. I mean, the number of the kind of tools that we use. Let me do it very quickly. Adrian, how much was the time in principle? I didn't ask you.
You have
15 minutes?
5 more minutes if you want.
Okay, let me do it quickly.
Yeah.
The spectrum of the d-dimensional sphere is very well known, is present in many books. There are certain eigenvalues that have a very explicit expression, and the multiplicity of these eigenvalues are the dimension of the space of homogeneous polynomials of degree k in d plus 1 variables, complex polynomial, that are harmonics, okay? The famous spherical harmonics, okay? They are this. I put Rn in the sense that it's the Laplacian of the Euclidean d plus 1 dimensional space. It's not the Laplacian of the sphere. Okay? It's another one. So they are related in a very strange way. And when you quotient and you have some spherical orbifold, might be a spherical space form or not. It doesn't matter if gamma acts freely or not. You have the same, except that the same eigenvalue, except that the multiplicity change. Okay, you only have to take care about spherical harmonics that are invariant by gamma. Okay, invariant by gamma means this. And well, I have not much time, so let me go very quickly. Aikida introduced, this is the main tool of both of papers. Introduce this power series, generating function, right? Now that the kth term of this power series is precisely this dimension, which is the thing that characterizes the spectrum, okay? We said that the eigenvalues are the same, only the multiplicities are affected by gamma, by quotient by gamma, okay? So we put this number are so interesting and are parameterized by non-negative integer numbers. And we put in a power series. This is a very usual way in combinatorics. And well, we prove this expression. Doesn't matter what it is. And again, this is the sum. You sum over not every element. You divide the sum depending on the number of depending on the order of the elements. Okay, and the main point is the spectrum. This must be clear. The spectrum, the two spherical orbifolds are isospectral if and only if these two numbers are the same for gamma and gamma prime, right? Because it's the only thing that affects the subgroup gamma in the spectrum. And this number will be the same if and only if these power series are the same for gamma and gamma prime. Okay, so this is clear, and this is a bit more complicated, but the point is you can do it for every dividing by the sum by the order of the elements. You do this, okay? And for a length space, in the particular case of a length space, you have this expression, okay? I will not explain, I am not explaining everything, but I wanted to show what kind of tools we use to prove the theorem. These are rational functions, right? Because now that these are polynomials in the denominator. So they are rational functions. Are meromorphic functions are rational. Okay, and the proof of the main lemma goes more or less in this way. Suppose you are with the length spaces that you have already add these parameters, the concatenation of this strange sequence of numbers. Okay, remember this is a representative set of all units in zeta Q. So when you apply this formula for the length space, you obtain that here. Suppose let's assume, to make it easy, let's assume Q is here should be a K. Should be a K, and I want to assume that this Q. Sorry, this is a mistake. Assume K is equal to Q. So you have to sum over the H such that are coprime to Q. This must be 1, okay? And if this is 1, remember the tail J are coprime to Q, and this H is again coprime to Q, okay? And what is this? Okay, you are getting here all the union of these elements are all co-root of unity, primitive co-root of unity. So what you get is the cyclotomic polynomial. Okay, this is something from number theory. This is the kind of tool we use. Okay, so the main thing here is that all this term that was added by this part of the coefficient of the parameters evolves to this, and does not depend on S. Okay, and well, what you get is you get the function, the generating function associate again. Should be K, and you get this. So if you have two isospectral length spaces with parameter S and S prime, if these will be equal if and only if these two will be equal. And this is exactly what says here. If these two length spaces are isospectral, means that these functions with parameter S and S prime will be the same for every K. But if these are the same, this will be the same when here below you have an S prime. Okay, and this means that these new length spaces are isospectral, and this is the idea of the main lemma, and the idea was to show what kind of tools we use. Okay, that's all. Sorry. Thank you very much.
Okay. Thank you, Emilio, for a very nice talk. I'm uploading here. You can do it there with the emojis. Okay, then. Well, are there any comments or questions for Emilio? Yes, Enrique and Paul. Well, let's start with Enrique.
Okay. So, Emilio, obviously, I'm not a specialist in this.
Me neither.
I'd like to take a step back and kind of ask you about the isospectral problem in other contexts. So obviously today you were interested in the spectrum on functions, as Adrian asked you in the beginning. More generally, one could consider the partial Laplacian acting on differential forms, for instance, right?
Yes.
But I was going to ask you, what about the context of geometric structures, right? So consider a given geometric structure on your manifold, which is some reduction of the frame bundle. Yeah. This is equivalent to a homogeneous section, right? That's a section of the frame bundle quotiented by your symmetry group. And you certainly have a Laplacian acting on that. So I was kind of wondering whether you know, or what's the kind of state of the art in terms of trying to understand geometric structures from the spectral perspective, right? So when are they eigensections of the Laplacian, as homogeneous section? And it seems to me the kind of algebraic question that people from your community would be well equipped to study.
Well, here probably is a personal opinion. Okay, my personal opinion is that the spectrum, maybe at the beginning, people thought that the spectral information, the sound of a Riemannian manifold or the drum, could say a lot about the form, the shape of the Riemannian manifold. But after several counterexamples, the idea is that you cannot hear almost anything. excepting the volume, excepting the total scalar curvature dimension, not much more. Okay, there are many open problems. You cannot hear, for instance, whether some manifold has constant sectional curvature. You cannot hear that until in dimension at least 6. You cannot know whether only from the spectrum you cannot hear this. And well, one possible question in your related to your question would be: can one hear whether some manifold admit a G2 structure, for instance, or a Keller structure or something?
Yes, indeed.
And in the case of G2, I don't think somebody studied, but it is known that one cannot hear whether some manifold admit a Keller manifold. There are already examples of one Keller manifold isospectral to something that does not admit any Keller manifold. Okay, for instance.
This is very interesting, because the question really, now that you set it up in that way, let me make the question much more precise.
Okay.
The question is, can we hear the torsion of a geometric structure? And the counterexample you just gave is very interesting, right? Because you would be saying, we cannot hear torsion free. Right? That's in the case of SUN structures. I don't know what's the dimension people proved it for. Is it we can't hear Kayla in any dimension, or just in 2 dimensions, or for surfaces, SU3? What's the dimension of that?
I don't remember. I remember the dimension can be arbitrarily large, but not remember what is, for instance, the smallest dimension. I'm not sure whether for dimension 2 is done. Okay, but I don't know. But concerning the other structures, I don't think anybody have studied this kind of question. But what one should do is start with the many ways to construct isospectral manifolds, for instance, Unada's method, and try to produce one satisfying this, admitting this structure, and the other not. This will be the approach.
Yeah, just to make just to be precise, and it's not so much whether they admit such a structure or not, because that's a very, very fine topological abstraction. It's more like, do they admit such a structure with such and such type, special type for the torsion, right? That's when we hear special torsion, that's where I think your technology should be able to sort of be adapted, right? Because it has to do with studying the Laplace and acting on homogeneous sections, right, which both have a representational description, right, and then trying to see whether the torsion being special has any spectral consequences. And from what you're telling me, then it's not the case. In several cases we don't know, but we know that it's a program that cannot be always successful because there's a K counterexample.
Yes, exactly.
Okay. Exactly. I'll think about it. Maybe if I have anything smart, I'll tell you in a year. But I feel motivated by your answers. Okay. Thanks.
Okay. Now Paul has a question. Paul Schwan.
Yes. Yes. Hi. One second.
Hi, Paul.
Hi, Emilio. Very interesting stuff. I was going to ask. It seems like the spectrum of these spherical manifolds or orbifolds are reasonably well understood. Do you know, or do you think if this machinery could also be applied to hyperbolic orbifolds, or do things break that completely? Can we access their spectrum somehow?
No, definitely not. In the hyperbolic case, that has been much deeper studied. Most of people have studied the hyperbolic case instead of the spherical case. in this case, you cannot make or write the spectrum as explicit as in this case. Moreover, you cannot write almost anything about the spectrum. Okay, it's the completely opposite case. And indeed, with Benjamin Linovitz, that is an expert in the hyperbolic case, we start our project asking or looking for things that have been studied in the hyperbolic case, but not in the spherical case. And the thing is that those that we were able to respond, the proof were not very difficult. It's like they are not analogous. I mean, if something is difficult in the hyperbolic setting, it is not necessarily very difficult in the spherical case. Okay, and well, this was the philosophy of this project. But knowing in advance that the cases are very, very different in this way. The spectral descriptions are almost impossible in the hyperbolic case, but in this case are very explicit.
But are there any things known about isospectrality of hyperbolic manifolds at all?
Yes, no. Many things are known about this. There are examples of hyperbolic surfaces, isospectral, and hyperbolic spaces too, but the machinery is very different. They are always related with number theory in some way, okay? Because they are arithmetic hyperbolic manifolds. Arithmetic is because they are constructed with something coming from number theory, like quaternion algebras, for instance. Or I remember Benjamin Linovitz came to Cordoba and gave a very nice lectures about the isospectral hyperbolic manifolds. I haven't worked in this setting, but I know it's very difficult. But there are many things known about this case.
Sounds fascinating. Thanks.
Okay. Are there any other comments or questions? Maybe I can ask these subgroups which give rise to orbifolds. In this case, are they classified?
No, I'm not sure whether it has sense to classify this because,
No.
I mean, every finite group. Maybe I'm wrong, but any finite group can be embedded in a symmetric group, right?
Yes.
And the symmetric group of n letters embeds naturally in the orthogonal matrices with the rank n.
Oh, okay.
So any finite group will give you at least one spherical orbifolds, but probably it will give you many in several dimensions and acts in different ways.
Yeah. Okay.
Non-isometric in one fixed dimension. So I'm not sure whether it has sense to classify.
Yeah. Okay. And the other thing about this lemma that you have with Linovitz, I guess, do you say something about the isospectrality on P forms?
I studied a lot this case. It has been already 5-6 years. But yes, I actually made a computational paper.
Okay.
Computational in the sense that I put the machine to look for examples and to know exactly which P isospectrality can be realized among lens spaces and which not. Okay. And the idea of this paper is whether I see some evidence of some result, I try to prove it, or I conjecture, or I do something. But yes, it is known a lot. Let me mention something that is known. Was the main contribution with Juan Pablo and Roberto, that we prove that there are length spaces that are p isospectral for every p, but they are not isometric. But they are not, sorry, they are not strongly isospectral, which means strongly isospectral means to any manifold you can associate natural bundles, and in this bundle, natural operator, natural Laplacian, okay? And the Nacional, for instance, gives you not only isospectrality on functions, gives you isospectrality on any of these natural operator on natural bundles, okay?
Very strong.
That's strong. And well, for instance, the Hodge Laplacian are natural and the Lichnerovich Laplacian are natural. And well, at some moment, some people thought that p isospectrality for every p, the Hodge Laplacians, implies strong isospectrality. And we gave counterexamples of that because the length spaces cannot be strongly isospectral and they are p isospectral for every p.
Okay. Oh, very nice result. Okay. Well, are there other questions or comments for Emilio? Okay. Well, if that's not the case, let's thank him again for this very nice talk. Okay. And for his accepting in a very short period of time. We invited him 2 weeks ago and he said yes immediately. So thanks again for that.
Right. Thank you, Emilio.